Lab 2, Lines of Charge, Physics 2212. The purpose of this lab was to create a more accurate estimate of the magnitude of charge on one piece of tape using a more sophisticated model than the point charge model used in Lab 1. In order to do this, we used a floating tape setup and split the two pieces of tape into line charges and then used a guess-check method to solve for Q. From this, we gained the results that the magnitude of the electric force on one piece of tape was 1.96 times 10 to the negative 3 coulombs. Within this lab video, I'm first going to go over the main concepts, the experiment, the calculations done within Lab 1, the glow script code for Lab 2, and the discussion questions. The main concepts used within Lab 2 were the electric force, which is the attraction or repulsion between two charged objects, Newton's third law, which is for every action there is an equal and opposite reaction, as well as Coulomb's law, which states that like charges repel and opposite charges attract. For this experiment, we created a floating tape setup similar to the one used in Lab 1, and for the length of tape I had 0.2 meters, the mass of my tape was 0.002 kilograms, the distance between my tape was 0.04 meters, then I was able to calculate the gravitational force as 0.00196, and I assumed that the same charge was represented on both pieces of tape and that this charge was evenly distributed between the pieces of tape. Using these assumptions, this allowed me to divide the piece of tape into equal pieces. For my first Q value, I used the Q value found within Lab 1. In order to find this value, I first calculated the electric force using the formula that the electric force equals the Q times the electric field, and then I was able to set the electric force equal to the gravitational force to solve for the excess charge. From Lab 1, I found that this Q value was 1.4 times 10 to the negative 8 coulombs. In order to code for Lab 2, I first created a model of two charged tapes divided into n smaller points to calculate the electric field and force interactions, and then I modeled two arrows to represent the gravitational and electrical force, and then used 10 smaller arrows to represent the individual electric force on each point in the bottom tape on the top tape. From this, I was able to get an estimate of the charge on the tape by adding up the electrical force at each point. The first thing I did within my code was to define the constant UFPES and the gravitational constant. Then I input my mass of my tape and the initial Q charge found from Lab 1. This Q charge was continuously updated using a guess and check method, and the final Q charge was found to be 3.3 times 10 to the negative 8. Then I used the electrical field function that was found in Lab 0 in order to calculate the electrical field. From here, I was able to use the lines of charge function that was given to us within this lab in order to model the two pieces of tape as lines of charge. From there, I modeled the two pieces of tape as spheres for the bottom tape and the top tape. I then was able to use this for loop given to us for Lab 2 in order to represent the forces exerted onto the top tape by the bottom tape at each individual point. Lastly, I represented the net electrical force and gravitational force by two larger arrows. Here are my results, and you can see the larger arrows for the electrical force and gravitational force, as well as the smaller arrows, which is the individual electrical forces exerted on the top tape. And then you can see that my final electrical force was 1.96 times 10 to the negative 3. So for the lab questions, the magnitude of the charge on one piece of tape was 3.3 times 10 to the negative 8 coulombs, and the assumptions I made within this lab was that I could ignore air resistance on a moving object and then assume that the U-tape I created had the same amount of charge evenly distributed along the length of the tape. The first discussion question asks, what if you had modeled each piece of tape as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So for Lab 1, the charge value I got was 1.4 times 10 to the negative 8, and for Lab 2, with the line charge model, I got 3.39 times 10 to the negative 8. If I had used a point charge model again within Lab 2, I would have received the exact same value for Lab 1. The next question is, why do these estimates differ? Which value is more likely to be closer to the real value, and why? The line charge method is going to be more accurate than the point charge model, and they differ simply because the line charge method is a lot more accurate than the point charge model. The line charge method utilizes the superposition principle, which is a much better representation of how actual charges interact. In conclusion, this lab showed that the superposition principle can have a very significant impact on the net force, so regardless of how small the force is, it's very important to consider it in order to have a more accurate model.